Hey everyone! In this video I'm going to continue my overview of basic functions and programming in R. In the last video I showed you RStudio Cloud and how you can follow the code that I'm going to show you here, which is also the code that is in the EMI textbook to keep it simple. But you can directly kind of follow the code step by step and run it in your own RStudio Cloud project. So as I mentioned in the last video, we can use R as a basic calculator, which is kind of the most basic way of using R, would be to use it as a calculator to kind of, for example, let's see if I can add two numbers, or basic division, or compute 5 to the power of 3, and then the console will show you the respective results. Okay, so those are the basic mathematical operations that you can run in R. Of course, these can be a little bit more complex, right? So you can have parentheses and longer mathematical formulas. You can also, for example, compute the square root. Here using the SQRT function. This is an example of a function in R, and we'll talk a little bit more about how these functions work. SQRT is, of course, the square root of 4, and that is 2. In general, of course, this is not everything R can do. The important thing is that in general, whatever transformation and data or computation we're going to try to execute in R, we want to save those in some kind of object to use it later on. And in general, R can store information as different types of objects, and each of these objects have a name that we can basically choose, and with that name, that object is then saved in our workspace in the current environment. In order to assign some value to an object, we can use the assignment operator. This is this little arrow, so smaller, and then minus. We use that to assign some value to an object. So here's an example where we look at the sum of 5 and 3, and we can save this in an object now called result. Right, now every time we call result in the next line, we just call this object. It will return whatever the result is of this computation, 5 plus 3. Another way of kind of extracting this or showing this in the output is using the print function. In our case, this doesn't really make a difference. We can just call the result or use the print function, but in some cases, as we will see probably later in the semester, sometimes we can, it helps to be explicit about kind of printing the results to the console. One thing to pay attention to is that if we assign a different value to the same object name that we defined before, then the old value will be overwritten. And this is really important to keep in mind, because you can lose data that way. If you're not careful and you just override an object that you already declared previously, and then just, for example, now compute 5 minus 3, then of course, if you call result, the original computation is then lost. You would have to run the command again. So this is just something to keep in mind. If you handle a lot of different objects, you have to be careful that if you overwrite them, that you lose potentially information. Okay. Another thing to keep in mind is that these objects can have different types. They contain different types of data ultimately, right? So in the examples that I showed you before, it's all numeric values, but it doesn't have to be all numeric values. So for example, it can be character strings that can be contained in an object, right? So in this case, right here, I'm showing result as 5, but 5 now, as you note, is in quotation marks. And this is actually, this might seem subtle at first, but this is actually an important difference, but because now this 5 is not saved as a numeric value, it is actually saved as a character string, okay? So if we call this result, we'll see 5 now is again shown as 5 in quotation marks, which indicates that this is actually a string, not a numeric value, okay? And this can be important because if we now, for example, try to divide result by 3, R will give us an error. If you look here, this would be the output. Because 5 is saved as a character, not a numeric value, and you can't divide, a string by a numeric value. So even though the underlying data you might think is, for example, if you load external data files, sometimes certain variables are coded in the wrong kind of data type. And so you have to be careful whether your numeric values are actually loaded as numeric values, or maybe they're loaded as strings. And if they are loaded as strings or other types of variables, then you can run into trouble. So what is going on kind of under the hood is that R recognizes different types of objects by assigning each object a certain class. Okay, so, and this is just another detail to note here. I called both objects here result, but one was result with a capital R, one was result with a lowercase r, and these are distinct, right? So object names are case sensitive. This is another important thing to keep in mind. Result uppercase R is different from result lowercase r. So if we call result lowercase r in R or RStudio Cloud, we'll still get the old result of 2 that we had that we computed previously. And if we're not sure how R saved a specific data type, we can use the class command here, class result, so that R tells us what type of data is ultimately saved. So in this case, if we call class parenthesis result, we'll get the information that this is a numeric type. So this is numerical information. If we did the same thing with result capital R here, we would get character as an output of the class command. Oh yeah, and this is what we get. Same for result. As I said, here you see the difference. In parentheses 5, here it's a numeric value, just 2, and the output of class result is character. So this is a string and not actually a numeric value. And the next very important structure of data is that objects are not only just individual pieces of information, like an individual number or an individual character, but we can actually organize them together. And one basic way of organizing multiple values together is to save them in what is called a vector. And a vector is basically just a one-dimensional array that contains multiple elements of the same type. Okay, so in the example in the book, we kind of saved a vector that stored the world population estimates between 1950 and 2010 in thousands in a vector that we call world.pop, so population estimates of the world. And as you can see, in order to add these together in a vector, we use this little C command and then add each individual number separated by a comma. Okay, and then if we call this object, we'll get a vector, an output with multiple elements in each individual numeric value in one as one element ultimately. All right. Oops, that's too far. So we can save multiple elements together. What is important is that we can also select individual elements of a vector And we can do this using this bracket notation. And we'll use this quite extensively throughout the semester. So for example, if we call world.pop in bracket 2, that means we want to select the second element of that vector. If you look at the vector originally that we saved here, that's 302,000 or 3,026,000, but this is in thousands, so 3 billion. And this is the value that we get if we just call world pop in brackets 2. We can also add multiple elements that we want to extract. So for example, here we kind of combine two things. We have a vector C 4, 2. And so now what we're doing is we're extracting the fourth and second element of our world.pop vector. And note that this is also changing the order. Now we have the fourth element first and the second element second. Okay. Another way to select elements is we can also just exclude specific elements. So for example, here we have world.pop -3, which means we're including all elements except for the third. Okay, so we have now a vector that is of length 5 instead of length 6, and it just excludes the third element of the original vector. And vectors are really important because they allow us to basically simultaneously perform operations on each element of that vector, right? So for example, this was the world population in thousands. We might want to save this or change this to change the scale to save this as the population in millions rather than in thousands. And so in order to do that, we can divide the world population by 1,000. So that means every element of that vector is now divided by 1,000. And if we look at the results, this is exactly what we get. Now we have the population estimates in millions. So dividing a vector by a scalar, so by one single number, means that we divide every individual element of that vector by that specific number. Okay. We can also do that by using elements of the vector itself. So for example, here we're now dividing the vector world.pop by the first element of world.pop. So what does that mean? What are we getting? We're dividing, remember this is kind of a time series of estimated world populations. We're dividing every element by the first element in that vector, which is 1950 estimated world population. So ultimately the result will be the population rate relative to 1950, right? So in 1950, of course, it's 1, and so we had a 19% increase in the population from 1950 to 1960. As I mentioned in the previous examples, we perform the exact same operation in each cell. So we kind of multiply or divide, in this case, divide by a certain single number, and so we basically just repeat the same operation with each cell. This does not have to be the case, especially if we work with two separate vectors. So in this example, what we're doing, we're creating a new vector called pop.increase, and this is now defined as world.pop -1. So we remove the first element, so 1950 world population, and then subtract world pop and then subsetting to exclude the seventh element, so the last element. So if you think about what is going on here, kind of how these elements are matched, now we have two reduced vectors, and in each element we're basically kind of subtracting the first element of the first vector minus the first element of the second vector. And in the second element, we're subtracting the second element of the first vector minus the second element of the second vector. And given that we removed 1950 from the first vector and removed the last part from the second vector, what this will give us is the increase in the world population from 1 year to the next year. Okay. In the next line, we're using this pop.increase vector that we just computed and divided by the world population in each specific year, and then multiplied by 100. So what will this kind of result in? Ultimately, this will give us the percent increase in the world population from one decade to the next decade. Okay, and this is exactly what we see here. Of course, we have here the 19.8% that I mentioned earlier, and then from 1960 to 1970, 21%, and then so on, 20%, and so on. Of course, these numbers going forward are different from these numbers up here, because here we're looking at the population rate always relative to 1950. Here we computed the change in population rates from going one decade further relative to that decade. Okay, so it's a different baseline. I just realized that wasn't in full screen. Another important concept in R that we're going to use basically every week is functions. And functions are they're a type of object, and they're a very important type because they allow us to perform a wide range of tasks, and essentially they allow us to efficiently repeat complex transformations or computations many times by just kind of giving the function a certain input or a number of inputs, and the function will kind of do the same or kind of do the same sets of operations with these inputs, and then return some kind of output. Okay, and we already saw some examples like the square root command that I mentioned, or the function that I mentioned early on. But there are a whole range of functions available. For example, length, which will give you the number of elements in a vector. So if you type in length and then word pop, it will give you the length of that vector. Min returns the minimum value in that vector. Max, of course, the maximum value. Range gives you the minimum and the maximum right away. We can also compute the mean right away, which of course we could also compute manually by summing all the elements in that vector and dividing them by the number of elements in that vector. And that, of course, gives you the same result. It is important that in the examples that I just showed you, the functions always took just one input, but this doesn't have to be the case. We can have multiple arguments that we enter into the functions, and we can return one or more outputs as part of that function. So one example for that is the sequence command, which allows you to create numeric sequences following a certain structure of certain rules. So for example, we can create a sequence that ranges from 1950 to 2010 by 10, which means ultimately this will create a vector of numbers that starts at 1950 and then always adds 10 up to 2010. So the resulting vector is a 7-element vector with decades or numbers from 1950, 1960, 1970, and so on. The important thing is that here we have 3 different arguments that we enter into the functions, and these arguments are named. So specific functions allow specific types of arguments, and you kind of have to see, depending on what kind of function you're using, how exactly these arguments are supposed to look like. I'm going to show you later in an example of how you can find out how these arguments are named and how exactly they can be used. So going back to our vector of population estimates, one thing to note about vectors is that we can also name the elements, which can often be very helpful to kind of have a better overview of what the underlying data actually is. So if we look at the names of this world.pop vector, first, the result is null, so there are no names attached to the elements in that vector. But we can assign new names by using our new year vector that we just created. And then we see after assigning year, this vector, to our names world.pop, now we have a vector of string of character values containing these years. And now if we call the original vector world.pop, we see that now it's not just a list or a vector of numeric values for the world population, but actually each element has a label attached to it. So functions are incredibly important, and one reason why R is so powerful is that it's very easy to write your own custom functions, and we'll go through some examples throughout the semester as well. In general, the structure of kind of defining a function is always the same. First, we give the function some name. In this case, it would be my function. Then we include this function argument, and then include the list of arguments and inputs that you can include. And again, similar to the sequence command, this can be a set of arguments. Then there are a couple of operations or computations that can be done with this with the inputs that were kind of passed into the function, and then there's an output that is returned. Okay. To give you a more concrete example, here's one, a custom function that returns several summary statistics based on one single input. Okay, so we call this function my.summary right here. This has one input. We call this input x. Now within that function, we can refer to whatever input is passed to that function as x. And then we can compute three different summary statistics. First is we just sum up all the elements in X. We compute the length, or we just return the number of objects that were in X, assuming that X is a vector. Then we divide the average by just dividing the sum by the number of elements. And then we create a new vector called out, which contains basically the three objects that we just computed, s.out, l.out, and m.out. We can give those three objects names, sum, length, and mean. And then we return this in the end. And this is then what the function ultimately will return every time we call it. Okay. So here's an example of what this will look like. Here we create a new vector z that is just, this is now a shortcut for a sequence from 1 to 10, going in steps of 1. And so, for example, if we compute my.summary for this new vector z, the sum of all integers 1, 2, 3 up to 10 is 55. The length of that vector is 10. And the average is 5.5. You can kind of, if you want, check manually whether this is correct. We can also do this, for example, and this is kind of where this is so powerful. We now have a function where we can give it multiple inputs, different types of input, and it will just compute the same, sets of computations. For example, we can do the same thing for the world population. Look at the sum, the length, and the average of that object. And of course, these functions can ultimately include much more complicated computations and go through a lot more different steps. And this is why this is incredibly useful and powerful going forward. All right, another important topic to talk about is external data files. So in a lot of cases, of course, we're not just manually creating vectors of numeric values, but ultimately what we're doing in our research projects is that we're importing external data files like survey data and the like for our analysis. And R has the capability to read in a wide variety of these data file types. So as I mentioned in the last video, I included some data sets in the data folder in the shared workspace for this for this lecture code. And so if you want to, for example, read in a CSV file, which is a comma separated file, it's kind of like a simplified. You can open it in a text editor, and essentially the way this file type works is that each row is kind of one observation, and each variable in each column is just separated by a comma. That's why it's comma separated. Okay. So for example, any Excel file that you have, you can save as a CSV as well. So if you want to read in such a file, you can use the read.csv command. We save this in a new object, and if you look at the class of this new object, this will be a data frame. And a data frame is actually a type of object that is more complex than a vector because it's essentially an n by k matrix where each row is one observation and each column is a specific variable. And we'll use most of the data types that we'll work with will be data frames in our case. We can also load R data files, .r data. They're slightly different in the sense that R data files can contain not only one data frame like a CSV, but can actually contain all the objects that we might have in our workspace. And there are other types of external software like Stata files or SPSS files that we can read in as well. If we have a data frame, what is important to note is that this data frame, the variables are named. So for example, if we look at the names of U and POP, the data frame that we just loaded, we can see that one variable is called year and one variable is called word.pop. It's the same data that we used before. And we see that we have seven observations and 2 columns, so 2 variables in this data file. If we look at the dimension, another command that we can look at is dimensions, and this directly gives us the number of rows and the number of columns, or we can call the data frame right away and we'll see the underlying data, which is the same data that we worked with previously. So when we're working with data frames, there are a couple of additional commands and a couple of additional things that we have to take care of. We can look at a summary of a data frame right away. This will give you a short overview kind of every individual variable that is included in the data frame. In our case here, year, and it will give you the minimum, median, mean, and so on, and world population. If we have a data frame, we can access specific variables included in that data frame using the $ operator and the name of the variable. So if I call unpop $world.pop, ultimately what R will return is the vector that is in the world.pop column in the unpop data frame. Okay. We can also create new variables and add them to the data frame. So for example, here I'm computing again the population in millions based on the original world.pop in the unpop data frame. But here I'm saving saving this as a new variable in that data frame, right? So similar to vectors, we can also use these bracket operators to select specific elements in a data frame, but note that the data frame is a two-dimensional object, so it's not just one dimensional like a vector. So we have to if we use the bracket operator, we have to kind of select both dimensions, the row and the columns, so to speak, and separate them with a comma, right? So for example, here we select unpop and then in brackets 1 from 1 through 3, so the first 3 rows of that data frame, and then we have a comma, and then we only select world.pop.mil, so the world population estimates in millions, and then we'll get a 3-element vector which contains this newly computed world population in millions. Another important topic in R and working with data frames, especially with survey data, is that oftentimes we have missing values on certain variables. And in R, these missing values are represented by NA. So sometimes when we're, for example, computing averages or doing some other computation, we have to remove missing values from a vector when running these functions. So for example, here I'm just adding a missing value to the vector world.pop. So now we see there's an 8th element here, and that is a missing value. And if I now compute the mean of that world.pop, we see the result is actually now a missing value as well. The reason is that as soon as there's one missing value, basically R says, okay, you want me to compute the mean. The mean is the sum of all the elements divided by the number of elements, but one of the elements, I don't know exactly what number that is, so I'm not going to give you, a value, or I'm not going to be able to compute a value. If we want to tell R in this case that it can ignore these missing values, we have to add an additional option in the mean command, which is called na.rm, so na remove equals true. And if we include that argument in our mean call, then we get again the average that we computed previously in the example. As we're working with transformed data sets, in some cases we might also want to save our data sets or transform data sets in new files for later use. So for example, we can, and there are different ways to do this, to achieve this. We can save the entire workspace that we've been working with as an RData file using the save.image command. We can also save individual objects as RData files, so not the entire workspace, but just, for example, now we worked with the unpop object and the year vector. So unpop is a data frame, year is just a vector, and we can save that as an RData file. Or we can save one data frame itself as a comma separated file, for example, using the write.csv command. So this is now just one data frame, and it will be then saved as a CSV file. In general, just a note of caution, as a general rule, never override your original data sets with your process data, right? So every time you're working with external data, I want you to kind of keep the original data in its original form, keep it intact, and save the script that contains all the transformations and computations that are necessary for your project. Because if you don't do that, what is the problematic thing that might happen is that you're deleting some of your observations, or you're deleting some variables, or you're performing some computations that ultimately in the end you might not be able to reproduce exactly what happened, or you lost some data that you first thought you don't need, and then all of a sudden you realize, okay, maybe I should have used that variable, and if you're not careful, then these data might be just lost forever. So as a general rule, best practice, never override your original data set. If you need to save your process data, save it in a new different data in a different file, but always keep the original data intact, and always keep the script that contains all the transformations and computations that you did nicely documented as well. All right, the last thing for now is packages. So as I mentioned, one of R's great strengths is the existence of a large community of R users who contribute various functionalities as R packages. Right, so there's a huge community, and as soon as new methods or new algorithms or whatever you might think of are developed, people in the community kind of write packages that allow you to share these functions with other people. And so in order to kind of leverage this, we have to install and load additional packages that kind of give us additional functions and additional capabilities in R. The way to install packages is using the install.packages command. So for example, this is just foreign is installed on your in RStudio Cloud already, but if you have a new package that you want to use, you can install it using this install.packages command. Note that you only have to install each package once it's installed, and in your system you don't have to install it again. So in your script, I would recommend not to include these commands of install.packages at all. Just install it once, and then you have it in your on your system. What you do have to do every time you load or you start a new project or you start working on is you have to load the package, right? And this you can do using the library command. What this does is the package, not every package is directly loaded and directly accessible, but if you want to use specific functions that belong to a package, you have to load the library to make it accessible in your current environment, basically. The foreign package is a useful package to help you read in external data files, for example, Stata or SPSS files. For example, you have the read.dta command to load a Stata file, or we can also write write or save a data frame as a DTA file. If we want to share it with someone who's using Stata, for example, we can do that using the write.dta command. In general, if you're unsure how a command works, you can always get help using the help command. So for example, if you have no idea how read.dta actually works, you can look at help parentheses read.dta or question mark read.dta. Those are both equivalent. If you try this in RStudio Cloud, you'll see in your not in the console window, but in the window where you have the browser and where you see the different folders in your current working directory, you'll see a little window with documentation of how a function works, what types of arguments can be included as inputs, and what kind of outputs you can expect if you use that function. Another useful thing is if you install a new package and you want to see an overview of all the commands in a package, you can use the help and then in parentheses package equals foreign command, and of course foreign replaced with whatever package you're ultimately installing. So this is it for now. This was a little bit longer than I hoped, but I hope this is useful. As I said, please go through the code on RStudio Cloud and go through all the commands and play around with it a little bit. And in the next video, I'm going to talk more about reproducible research with R Markdown and knit R.